notes for AP Calculus on the topic of infinite geometric series. So remember, a series is indicated by the Greek letter sigma here. And the number at the bottom tells you where you're starting. In this case, n equals 1. Usually it's typically 1 or 0. And where you're stopping is indicated by the number over here, but when it's infinity, that's what makes it an infinite series. And remember, a geometric pattern is one that's defined by multiplication to get to the next term. So this one's just saying whatever that formula is for the geometric series, you plug in 1, get the first term, plug in 2, get the second term, plug in 3, get the third term, 4, and so on, and you add them all up forever. That's what makes it infinite, because it's going on forever. A finite one would not have infinity if there have a specific number. So let's look at a specific example here. In this case, we have a series from 1 to infinity of 3 times 2 to n minus 1. So we can tell it's geometric because we've got this constant as our base and our variable n is up in the exponent. So let's see what happens when we find what are called the partial sums of this infinite series. Partial sums are finite series. They're ones at n. So the first partial sum would be just using the first term. So if we find the first term by plugging in 1, that gives you 3 times 2 to the 0. When I take to the 0 power is 1 times 3, will give you 3. So the first partial sum, just using the first term, would just be 3. To get the next partial sum, you would be using the first two terms. We already got the first term of 3, right down here, and now we have to add that to the second term. So plus, the second term you would substitute in 2, the next integer after 1. So 3 times 2 to the 2 minus 1. 3 plus 3 times 2 to the first. 2 to the first is just 2 times 3 is 6, plus 3 gives you 9. So the second partial sum would be 9. That's the sum of the first two terms. And if you find the third one, the sum of the first three terms, well, we already figured out the sum of the first two terms here. A sub 1 plus a sub 2 is 9. So we can start with that. Plus, to get the third term, we would substitute in the next integer 3 for n. So it'd be 9 plus 3 times 2 squared. Two squared is 4 times 3 is 12, plus 9 gives you 21. So that would be the third partial sum, the sum of the first three terms. Okay. So you can see this is geometric because the terms themselves are 3, 6, so 3, we've got 6 and 12. So we keep multiplying by 2. Terms, so that's what makes it geometric. And for a geometric series, for an infinite one, some of them will converge, meaning they get closer and closer to a specific number, or some of them will diverge, which means they don't get closer and closer to a specific number. So in this case, you can see we got 3, we added 6, now we added 9. You can see we're going to keep adding bigger and bigger numbers, so this one would diverge. And the reason why it diverges is because what we're multiplying by, the constant ratio here is 2. Keep multiplying by 2, the numbers are going to get bigger and bigger. So when you try to add up all those different terms, it's just going to get bigger and bigger forever. So in order to converge, the requirement for an infinite geometric series here is the series converges only if common ratio, which we're multiplying by, is between -1 and 1. which you can see 2 is not between negative 1 and 1. Because if we multiply by a number between negative 1 and 1, then the opposite value of those numbers get smaller and smaller, so then they actually would converge. And if that's the case, then the formula used to get what that sum is just the first term divided by 1 minus that ratio. So let's take a look at a couple examples. So it says find the first 3 partial sums of the series and then state whether the series converges or diverges. If it does converge, find its sum. So let's find the first 3 partial sums again. So you get the first one. Be 4 times negative 1/2, 1 minus 1. 4 times negative 1/2 is 0. Anything that is 0 is 1 times 4 gives you 4. The first partial sum is 4. Then to get the second partial sum, we take that first one, which is 4, and we add it to the second term. And you plug in 2, 4 times negative 1/2. When you plug in 2 for n, 2 minus 1 is 1. So you just get 4 times negative 1/2. Gives you negative 2. So we have 4 minus 2. It's 2. So our second partial sum is 2. So that's the sum of the first 2 terms. And then the third one start with that 2, the sum of the first 2 terms, and add on the third term. 4 times negative 1/2. You plug in 3 minus 1, that's 2. 2 plus 4 times, when you square negative 1/2, 1 squared is 1 over 2 squared is 4. The negative goes away when you square it. So 4 times 1/4 is 1 plus 2 gives you 3. So those are the first 3 partial sums. And then to see if it converges or diverges, we could have told that at the very beginning. What we're multiplying by here, our base, is negative 1/2. So that's the common ratio we can often call R. And since that's negative 1/2, that is between negative 1 and 1. So we can find the sum. So that means this infinite geometric series converges. And since it converges, you can find the sum is the first term, a sub 1, over 1 minus r. When it converges, you can use that formula. We already found the first term is the same as the sum of the first term, which was 4. Right there. Over 1 minus r, we just figured out is negative 1/2. That's what we're multiplying by. So if we simplify that, that's 4 divided by, that becomes plus. 1 plus 1/2 is 3/2. And 4 divided by 3/2 is the same as 4 times the reciprocal 3/2 is 2/3. Which would give you 8/3. So that would be what this infinite geometric series converges to. It's getting closer and closer to 8/3 as opposed to infinity. Now let's look at one more here. It just looks a little more complicated to start with. So what I'm going to do first, notice we've got a 3 to the 2n minus 1 on the numerator and a 3 to the n on the denominator. Well, we can actually simplify those. Just think if you had x to the 7th divided by x cubed. Well, what would you do there to simplify? Well, you have the same base of x, so you subtract the exponent, 7 minus 3, and simplify to be x to the 4th. In a similar fashion, if you look a little more complicated, we can do the same thing here. We've got 2n minus 1 and n, and they both have the same base of 3. So just like we did 7 minus 3 there, to simplify this, we can go 2n minus 1 minus n. And what that will give us, the base still stays 3, is n minus 1. And then we still have over 2. So the formula actually simplifies down from 1 to infinity. So now let's find the first 3 partial sums. So we plug in 1. Plug in 1, that's going to be 3 to the 0 over 2. Anything that is 0 powers is 1, so that'd be 1 half. First partial sum. Then we take that and find the second partial sum. Sum of the first 2 terms is 1 half is the first term. Plus, now if you plug in 2, 2 minus 1 gives you 1, so 3 to the first over 2. Well, 1 half plus 3 halves is 4 halves, but that's just 2. So that's the sum of the first 2 terms. Our second partial sum. And then if we take 2 plus, plug in 3 there, you get the third term, 3 minus 1 is 2, so it'd be 3 squared over 2. 2, which is the same as 4 halves, plus 3 squared is 9 over 2. 4 halves plus 9 halves gives you 13 halves. Or 6 and a half would be the third partial sum. So notice on this one we're multiplying by, our base here is 3. And since the base is 3, that's not between -1 and 1, so this infinite geometric series is one that diverges. Keep multiplying by 3 when you get bigger and bigger numbers, trying to add those up, there's not going to be a sum. So when it diverges, that means there's no sum. You can't add it up. It doesn't approach a specific value. And that concludes the notes on the topic of infinite geometric series.